First of all, thank you very much to the organizers for inviting me here. I really enjoyed the conference a lot. I brought a lot of work to do during boring talks, but so far I didn't get any work done because I really enjoyed all of them. This is work that I've been doing for quite a while, as Neil said, probably because I'm stubborn or because I want to find out more. I've talked at the previous two meetings about these two papers with Leonard, where we identified a reasonable gauge structure and showed that it matches a particular superconformal model. Because I talked about this already, I'll talk about the progress that we made filling in some of the gaps that are necessary. So it will be a little bit technical, but I hope it will still be enjoyable, and there should be some interesting mathematical results along the way. So the conjecture that we're working towards is that it's classically a higher gauge theory. Of course, I know. Lots of obstructions, lots of counter arguments, but let me ignore them for the moment and follow rather Neil with this side. By hunting for unicorns, we may find other creatures that are useful in understanding the theory more generally. So that's kind of our guiding principle. And of course, the wish that we have is that we get the top thing, right? My daughters would be delighted. Of course, reality will be different. But the question is now, do we get something very, very sturdy, solid, reliable that looks different than what we expect, but that's probably applicable for a limited range, like 2 M5-Branes or something like this, just like this thing is now extinct? Or do we get an abomination of a physical theory like this that doesn't even do what we wanted to do in the first place, right? So that's the big question. So why think about the conjecture? Well, there's plenty of evidence and heuristic arguments. We have higher bundles with connections. We have 1-0 interacting actions that are kind of similar and match the picture. There are lots of problems. First of all, there are mathematical gaps, and there's most of this talk actually. And there are physical problems, and hopefully we can report on them soon. The summary is essentially we solve a number of mathematical issues, making interesting observations along the way. Hopefully they're interesting. And the rough perspective is the following. If you're a physicist, what we need is we need a higher analog of connections for higher gauge theory, because we think it's a higher gauge theory, so we need a higher analog of connections, also principal bundles, but that's not the big problem, so we really want decent higher connections. And then there's an issue there with higher gauge groups. There's a large group of equivalences, and physics should only see these higher gauge algebras up to equivalences, so we have to make sure that it doesn't see too much. Then we need a metric on these higher gauge algebras, so that can we write down actions. And we need a consistent definition of higher parallel transport. And all of this has now been clarified, I think, and I'll report on how this works in detail. Okay, so the detailed perspective is the following. I recall what probably should be a folk theorem, but I'm not sure to what extent it really is, namely that non-abelian gerbs with connections are locally abelian. I then tell you how this can be adjusted and how this can be resolved using string structures with connections as an example. And there's a nice Q derivation of the BRST complex that I hadn't seen before and we invented and might be useful for some people. Then I talk about metric string structures with connections in general. And then we can apply this into the models that we had before. The models previously had the PST mechanism to guarantee self-duality. That has various issues. It's not as nice. And now we replace it with Sen's new mechanism, and that's much more beautiful. And then I talk about adjusted high parallel transport, so how to really do this. And here the nice observation is actually a nice relation between 2-cross modules and L-infinity algebras, and what precisely, how these should fit together. And then one of the 3 big attack vectors that we're trying at the moment to get this theory under control, namely that we get actions from tree-level scattering amplitudes. Okay, so the alternative summary to the whole talk is that I'm doing adjustments to naive definitions, because if you believe in John Baez, well, we're using a lot of higher structures, higher category theory, and category theory is a subject where you can leave definitions as exercises, but the lesson that I learned from all of this is sometimes the naive definition or the straightforward definition are not the ones that you want, but you need for hidden or extended or extra solutions to your exercises that are actually also there. So that's the alternative summary. Okay, so first, need for adjusting higher gauge theory. Why would I want to adjust a higher gauge theory? Well, the summary is that higher gauge theories come with fake curvatures. For example, if you do the first extension with 2-form potential and 3-form curvatures, you get expressions like this, that your curvature is corrected by the B field, and you saw that in the tensor hierarchies in Henning's talk. The consistency of our usual definitions require this fake flatness, and this is too severe a restriction. It makes it essentially unsuitable for the 2-0 theory. And yeah, there's this folk theorem, namely that non-abelian gerbs with connections are essentially locally abelian and so not really interacting. I guess this is essentially what most people tried and where most people believe that higher gerbs, I mean, the standard argument that you hear is that non-abelian gerbs are not really useful in attacking this problem because they're actually abelian. I think this is behind it. I haven't found it anywhere stated explicitly in the literature. I talked to mathematicians who didn't know about it, so I thought it might be worthwhile writing it actually up. Later on, I found that a mathematician had actually proved the same thing rigorously analytically. What we are doing is we're just appealing to the standard non-abelian Poincare lemma in ordinary gauge theory. If you believe in this, then this proof goes through. And the way that this works is essentially as follows. So your gauge group is, let's assume it's a cross module of Lie groups. That's a good description of a higher 2 group. So you have this structure, you have an H, two Lie groups, and a Lie group homomorphism between them, as well as an action of G onto H. Few axioms, they're irrelevant here, that differentiates to a cross module of Lie algebras. And then you have potential forms where the 1 form takes values in G and the 2 form takes values in H. The fake flatness is then this condition. And now you have gauge transformations that act like this, and all this comes out of general nonsense. So you just plug these things in, and you essentially get these structures for free. And what you see now is that the gauge transformations and the gauge potential consistently restrict to G if you factor out by the image of T. You can show that the image of T is a normal subgroup of G. So actually, G is a principal bundle over G circ. And all this restricts nicely to it. But on this subgroup, here we have just f equals 0. And therefore, the non-abelian Poincare lemma tells us that we can gauge it away and obtain a gauge where a circle 0 is 0. Then you can show, and that's not too hard to do actually, that you can lift this gauge transformation to a full gauge transformation on G. And so you have an A tilde, which is in the image of T, and that you can then gauge away with this new lambda transformation here, right? So you end up, after this consecutive 2 gauge transformations, with a gauge potential that's 0. And that immediately implies that the connection is abelian and B is in the kernel of T, actually, just because of the fake curvature condition. So that means essentially that the non-abelian gerbs that have been discussed by mathematicians and physicists in the literature with the gauge connection, they're good for Hauer-Edge-Simons theory. They still capture topological aspects, but they're not good for R2-0 theory. So they don't work. They have, they're essentially abelian. You can gauge things away locally, so that's not good. Okay, so what else? What other problems do you usually see? So this is our gauge structure if we did this naive higher gauge theory. If you do it really properly with 2-term L-infinity algebras, you have also this mu3, which gives rise then to the Jacobiator. And what you see that this appears infinitesimal gauge transformation. They don't close properly, but they close up to terms proportional to the fake curvature condition. Then you think, okay, I might be smart. I just use strict Lie2 algebras, and mu3 is just 0, as in the previous example. However, then you find that finite gauge transformations do not compose. So you always run into problems with gauge transformation. That doesn't work. Self-duality doesn't work because H equals Hodge H requires F to be 0 for covariance because the gauge transformation goes like this. So here you have the standard transformation that you expect. But then you have also transformation with the fake curvature wedge, the lambda, the 1-form gauge transformation, gauge parameter. And clearly, this is not necessarily self-dual. So unless F is 0, it's not guaranteed that your equation is covariant. And finally, you see that also in the paratransport, that if you define higher paratransport in the obvious way, then you get fake curvature should vanish for reparameterization invariance. Yeah.
Why is it called fake flat?
That was just an invention by Brane. He called this curvature fake because it was a combination. I don't know. Do you know more? Is there any?
It's the 2-form component of the curvature.
Yeah, exactly. Yeah.
Which isn't quite an ordinary 2-form curvature.
Yeah, it's not the complete curvature.
The actual 2-form curvature.
Exactly. Yeah.
The word is really bad.
Yeah, no, it's badly chosen, but it's somehow stuck. I should probably not promote it further.
But it is a flatness condition. So
Yeah.
this issue which you just pointed out, is just the issue that
I always interpreted the fake to mean it's not really flat, so that's why I'm asking.
Yeah, it's not completely flat, right? Because you still have the H form around. That's not flat, right? But why this particular component is called fake, right? You would essentially, what you see in these higher gauge theories is a nice structure that you have the top form curvature that's kind of independent, that's nice. And then you have all the lower form curvatures. And all of these are fake curvatures. And the higher analog of this consideration is that all of the lower ones have to vanish, otherwise your gauge transformations don't close. Physicists know that sometimes that the BRST complex doesn't close. It only closes off shell for these higher theories. This is essentially what this means physically, right? Okay, so we have lots of problems. One more basic problem, and this is probably what got Urs, Hisham, and Jim Stashev into this, is that certain particular algebraic definition is not what you expect it to be. So high gauge algebras, we'll always model them as L-infinity algebras. I don't give a definition. Everybody has their own definition in their head, and that's good enough for this talk. So you have higher brackets and so on. The appropriate equivalence, and this is the important point, for L-infinity algebras is not ordinary isomorphisms that you would naively define, but there's something called a quasi-isomorphism of L-infinity algebra. So they're vastly more general isomorphism class, right? Dually, we can describe them as differential graded commutative algebras. So what you do is you shift your L-infinity algebra, the whole vector space, the whole graded vector space, by 1 degree, take the dual and take the symmetrized tensor product. So you just consider functions on the shifted one. And then you have a differential. And the way that this works is just in a Lie algebra, it's very easy to see. So imagine that you have a Lie algebra, you shift it in degree by 1. The coordinate functions, the coordinate functions map this into R. So they generate this commutative graded algebra, graded commutative algebra. And then what is a vector field on this space? Well, it's a derivative with respect to coordinates. You multiply it by 2 additional coordinate functions because you want it of degree 1. Combine it with structure constants, symmetry factor for convenience. And then these structure constants are really the structure constant of your Lie algebra, and the fact that it squares to 0, so that it's really differential, just amounts to the Jacobi identity. And this has a trivial generalization to higher graded vector spaces. Okay, so L-infinity algebras I can also have as this Chevalier-Eilenberg algebra, and you saw them in previous talks. What I can also do is I can look at the differential graded algebra of the inner derivations, and then you get what's called the Weil algebra. And the way that this works is you shift it, and you saw this yesterday also in Vincent's talk, right? So, but there was a slightly different construction. So you introduce for every generator a shifted generator, and within this differential graded commutative algebra, you have a sub-algebra of those that are just generated by T of alpha, by the shifted copies. And then the invariant polynomials are just the subset here, the sub-algebra here that lie in this, together with the condition that the differential on them produces something that lies again in this horizontal subspace. Okay? So there's a definition of invariant polynomials. The details don't matter. What is important that this definition, if you write it down as you would naively guess it, is not compatible with quasi-isomorphism. So the right notion of equivalence of L-infinity algebras is not compatible with this definition, and that shows you that something is wrong already at an algebraic level, right? It's not just that our gauge structure is problematic, it's already the algebra that's kind of problematic. And the problem is with the definition of the Weil algebra, right? And all of this can actually be resolved if you use connections on string structures or the gauge structure that sits behind string structures in the first place. So the summary of the following section is the following. So you have for some L-infinity algebras, we can deform, and we call this an adjustment. We can deform the Weil algebra itself. And in gauge theory, the implication of that is that the curvatures change, and correspondingly also the gauge transformation changed. And the prime example for this are string structures. So remember, string structure original spin bundles with trivialization of the Chern-Simons 2-gerb, right? Spin bundle has a first Pontryagin class, and it defines a 2-gerb, and you want to trivialize that. So there are particular non-abelian principal 3 bundles, if you want, and they correspond to spin bundles on loop space. That's why it's interesting in string theory. And they can carry connections, and these connections allow for such an adjustment, or rather the gauge algebra that's behind this allows for such an adjustment. And the original definition of string structures back a long time, but then really the adjustment was discussed by Urs Hisham-Starshev in 2009, and there was a paper by Waldorf and others discussing that further. But this is exactly the best example to discuss these structures. Okay, so what's an adjusted Weil algebra? Remember, the Weil algebra arose from a doubling of the generators of the Chevalier-Eilenberg algebra. And what we want to do is we want to form the action of this differential, but we won't only allow deformation such that it vanishes if you project down on the Chevalier-Eilenberg algebra by putting all the hatted generators, the copied generators, the shifted generators, to 0. And what we wanted to do is that if you construct a gauge theory, that its BRST complex closes, so all the gauge transformations are nice, right? So that's essentially what we want. So we forget about the algebraic motivation at the moment because it doesn't completely fix it. But here, if you look at the BRST complex and we want it to close, then it kind of, well, yeah, this is what we're interested in at the end, ultimately. The result is, again, that the gauge curvatures, they get deformed, and therefore the gauge transformations themselves get deformed. So how do you derive quickly the BRST complex if you have such a L-infinity algebra and such a Weil algebra? Well, you just generalize AKSZ in a very trivial way. So the usual construction of Chern-Simons theory, for example, via AKSZ, is that you would take the Chevalier-Eilenberg algebra of your Lie algebra and you map it into differential forms on your 3-manifold. And you take also maps that are not grade preserving, so that you get also ghosts and so on. And on this mapping space, there's a differential induced by the differential on your differential forms, on your de Rham complex, of course, but also by your Chevalier-Eilenberg differential. And now what we do, because we leave the Chevalier-Eilenberg algebra invariant, but we deform the Weil algebra, we adjust the Weil, we just plug in here the Weil algebra, okay? And then you have here the Weil differential. You can certainly do that and just look what comes out. If you do that for Lie algebra, the structure that you get is the following. So for the generator T alpha, I get these fields. For the generator T hat alpha, I get these fields. And because it's an algebra morphism, that fixes the morphism completely, okay? What you see is, of course, that we have way too many fields, right? We have here the antifields. We just put them to 0 because we're just interested in the BRST parts. So this would give you the whole BV complex, but we just want the BRST part. So put these to 0, and we put additional gauge parameters to 0, and then you just have these left over. Okay, now you can ask, can I do this consistently? And, well, let me just show you what happens. If you do this and you plug all these red fields, you put them to 0, you get the transformation of the gauge parameter, you get the gauge transformations of your potential, you get the definition of your curvature, you get, where is it, the Bianchi identity here, and you get the gauge transformations of your curvatures down here, right? So you can all put this consistently to 0 and just tell you the whole kinematical structure, right? So in this way, you can really quickly derive the BRST complex, and then you can check whether it's closed, right? So you take your Weil algebra, you implement some deformation, you compute the BRST complex, and you see if it's closed. That would be a general prescription, right? Because this gives you the complete kinematical data. We don't want to impose any dynamics. So first, we're interested in potential, curvature, gauge transformations, and Bianchi identities. And this is what this gives you. Okay, so let's do that for Lie-2 algebra for such a structure, right? So now we have twice as many generators, 2 copies here and 2 copies there. So we have a T and a T hat from here and the shifted copy. We have an R and an R hat from here and a shifted copy, and you get this expansion, okay? Again, we put everything that we don't want to 0, all the redundant gauge parameters, all the antifields, we put them to 0. And then you get the usual potentials, curvatures, gauge transformations, and of course you see the problem with fake flatness, that this equation is only consistent in general if you put fake flatness, the fake curvature equal to 0. Okay, so now you can adjust this thing. But before I do that, I first look at a specific example, because I said this adjustment only works for specific L-infinity algebras, I would say. And the example I want to look at is R to G, right? There's a natural Lie-2 algebra structure, which is called the string algebra on this. But for later on, I want to expand this directly because it will be nicer. Remember that the string structure is a spin bundle together with the trivialization of the Trans-Simons gerbe. So I know that there's a 2 gerbe somewhere in the background, and this is why I would immediately like not to have just a 2 group or 2 algebra, but immediately want to extend it to a 3 algebra. Okay, so let me just allow it to extend this here. This certainly sits in this space, and yeah, the fact that I extended it by the kernel, you can always do that for any L-infinity algebra. Okay, so I have this Lie-3 algebra, and this is actually, in fact, quasi-isomorphic to the Lie algebra G here that sits in the first component by itself. The subscript just allow me to differentiate between the 2 different spaces so that you know where things are mapped to and so on. Okay, so I have a Lie-3 algebra, and I have an unadjusted action of Q for this Lie-3 algebra that looks like this, and I have an adjusted action of Q that looks like this. So there's an adjustment that's known, was worked out in detail, and what you have here is that you have always such a function. I called it here chi sk for skeletal. That will become clear later. And what it takes 2 of these hatted generators and modifies the transformation, right? This thing is what is later mapped to the first Pontryagin class. So this is really corresponding to a topological invariance. So that parameterized here, the deformation is really controlled by this function here. And in the skeletal case, it's very nice because it's just given by the killing form on your Lie algebra. Okay, so you always have this chi skeletal functions at this here and at this point, and makes the algebra structure a little bit simpler. Okay, so now you can derive the BRST complex, and you derive the kinematical data just as I showed. You get 3 gauge potentials as you would expect. You get your curvatures. There's the 2-form curvature, the 4-form curvature, FGH, now in alphabetical order for once, right? And here the 3-form curvature now gets modified. This is the usual term, and now you have this deformation chi-sk-af, and this is very beautiful because what it does, together with this term, it produces precisely the Chern-Simons term for you, right? And this is what people in heterotic supergravity knew already in the beginning of the 80s, that if you want to couple your B field to non-abelian potential, you need this structure, and they indeed have this whole kinematical data already in their papers, right? You get the Bianchi identities here, that looks very nice, right? The anomaly cancellation condition, and you have gauge transformations here. So you get everything out, and you can show now that the gauge transformation is really close, the BRST complex is closed, everything is fine, and all the nightmares, all the problems with the fake curvature, they essentially go away. Okay, so now our gauge structure is kind of nice, but if you look at this, it is not, well, we need a metric extension to write down actions, right? If you want to write down action principle, Lie algebras, I need to have a metric Lie algebra. Here I also want some kind of metric extension. And the appropriate notion of a metric on L infinity algebra is called a cyclic structure. It's just given by a symplectic form, right? The string algebra, though, is not symplectic. If you look at this, you have a hard time putting a homogeneously graded symplectic form on this thing, right? There's no way that you can do that. But what you can do is you can just extend it to cotangent bundle, or to cotangent space of this vector space. And what you're doing at the time, I had no clue about the BV formalism, so I didn't know what I was inventing there. But what you're really doing is just you imitate the BV formalism. You just introduce antifields, you pair them up, and then you have it, right? So that's really just to shift the BV formalism, and that's exactly what I suggested yesterday to Martin to do in his talk. Okay, so what do you do? Well, down here you have your original Lie 3 algebra. Okay, now you need this, you need to double it and turn it on its head and grade shift it so you can pair things up. And this is what these three things here do. So the G star pairs with this one, this pairs with this one, this pairs with this one, and this has a nice symplectic structure, you get an inner product structure, and that's all fine. But at the end of the day, we now changed the quasi-isomorphism class of this L infinity algebra, because if I just, this one down here was just equivalent to G, but by extending these two will drop out in cohomology, so I have G star times G. So it's very natural, actually, to have an additional G star added here, just to make sure that the whole thing, the whole complex, again, collapses in cohomology and becomes equivalent to G, because that signifies that it's quasi-isomorphic to G itself. Okay, and the interesting thing is that this whole thing now also allows for an adjustment, but you have to calculate, and this is the work, essentially, that we did, right? So this allows for an adjustment, and then you get the kinematical data looks like this, the curvature looks like this, so F and H don't get modified, but you see here the adjustment functions, the functions that control the adjustment, the Cartan killing forms, they appear here in various places, and you have to be careful how to interpret these, right? So there are various functions that appear here, but it's all controlled, of course, by, again, the same adjustment function. So we do have adjusted curvatures, and that's all very nice, and then we can try to build actions. Okay, but if you want to try to build supersymmetric actions, you have the problem that you have to do a lot of calculation, and that's very hard. So the first thing that you do is you look around in the literature what's already known. And there is actually a 1-0 action in 6 dimensions with, let's call it a mysterious gauge structure, right? So there was abstract gauge structure that had been derived in terms of vector spaces and lots of structure constants by Samplin, Zetsky, and Wimmer in 2011. And it's not that mysterious, actually. If you know anything about L infinity algebras, you look at the structure constants, you see rather quickly, well, there should be an L infinity algebra behind. But it's not just that on the nose. You see additional structure constants that are not present in L infinity algebra. But if you now go back to this stuff, and you have also this additional adjustment, right? This is function that controls the adjustment, that fits exactly their gauge structure. So their gauge structure is a generalization, if you want, of string structures. But I would rather say, well, the supersymmetry algebra didn't expose all the constraints. You should really specialize that model to string structures, and everything is well defined. So that we already did previously, but now what we can do is we can take the PST part out and replace it with sense mechanism to get something nice. Okay. So what does this 60-1-0 action look like? Well, it has been derived from tensor hierarchies in supergravity, so that's a very, very nice derivation, and shows again that supergravity knows so much about theories and of physics in general. They can be specialized to this adjusted metric string structures. We already observed this really early on. The field content that you have is a 1-0 tensor multiplet, a 1-0 vector multiplet. And now we just put all of these into the right subspaces of our higher Lie algebras, right? That works really nicely. You get 2 copies of the scalar field. Essentially, you get 2 copies of the tensor multiplet, and you get a vector multiplet taking values in Lie algebra plus this additional R that you have. You have an additional C field and an additional D field. The action schematically looks like this. It's really fully interacting. And you can also complete it supersymmetrically by adding a matter and PST sector to have the same field content as the 2-0 theory, right? So what have we won? Well, we know that this gauge structure that we derived is really properly defined mathematically. You can glue this together. We know the transition factors really at the situation where we have principal bundles, higher principal bundles with connections. So this is mathematically perfectly well defined, has a lot of physical issues. We can discuss them later, right? But in principle, mathematically, this is okay. And I can even put this on any manifold if you want, right? So in principle, I know how to glue these things together. There's no guesswork here from the mathematical side. Physically, of course, it's a different story. But yeah, that's kind of what we had. But then if you implement the PST action, you get this weird addition term that has 1 over the scalar field, and I'm still a little bit baffled. I should talk to Henning more about that. That seems to be a general feature of this PST mechanism. Of course, it's not nice if you try to derive physical consequences from that. So we need to get rid of this to study it further, and then along came, fortunately, Ashok Sen with this new mechanism that you already saw previously in Neil's talk. So the idea is, as Neil said, that you introduce an additional self-dual 3 form. You get 2 self-dual form, 1 decouples and the other one stays, as you saw previously. And we just take out our PST mechanism, shove in this new mechanism, and everything works, right? We do actually a little bit more because our desired equation of motion in this 1-0 model are the following. You want self-duality for H, modified slightly by fermions. But then you want, in addition, that this 4-form curvature has something to do with the 2-form curvature, right? There's an additional duality there, and you would like to impose this as well. And this is not a problem, right? So you introduce all these new Lagrange multiplier terms following Ashok's prescription. For example, you have this term then in the action, right? This H, curly H, is the old H corrected by these supersymmetric terms. And it fully replaces PST, and the equations of motion work. We have not completely finished the calculation for supersymmetry and so on, but I don't expect any further delay. So the PhD student who worked with me on this went on temporary suspension of study, so this is why it took a little bit longer than anticipated, but yeah. So this is in principle fine. Okay, so next issue. So I said that there's lots of technicalities here, and this is about strict metric string structures. I already mentioned that L-infinity algebras have this large class of isometries, this quasi-isomorphisms between them. And what you now want is that all these quasi-isomorphic models work. And in particular, for the stringly 2 algebra, there are 2 kind of extreme cases, a skeletal one that I presented above, and then there's a strict one that I discussed now. There's a general structure theorems that tell you L-infinity algebras are, any L-infinity algebra is quasi-isomorphic to a strict one and to a skeletal one, to a minimal model, right? And so we would like to see these 2 extreme cases because it will give us a nice restriction on how to construct physical actions. Our physical actions shouldn't see this quasi-isomorphism. So whatever action I should write down, it shouldn't care about which L-infinity algebra, which quasi-isomorphic representative of my L-infinity algebra I put into the action, okay? And I should have a metric adjustment also for the strict model, which will then give me constraints on the actions. Okay, so the strict model works like this. It might be interesting because it's, you get Kac-Moody central extensions that appear quite a bit. So the skeletal model was up here. So we had here a Lie algebra. We had just R. Differential is just 0. Mu2, the bracket is just a Lie bracket here, and mu3 is just the usual cocycle that you get from the killing form as well. Quasi-isomorphic to this, you can consider the based paths in the Lie algebra and a central extension of the based loops of the Lie algebra, and this has been shown by Urs, John Baez, Krantz, and Donny Stevenson. And then the structure here is that you just have mu2s, you don't have a mu3, and it just looks like this, okay? Also for the strict model, you can do the adjustment, and we should just calculate what it is. First, we do the metric extension. That gets now a little bit more complicated, but it's essentially the same idea. Just mirror this, flip it, and you join whatever you need so that it's quasi-isomorphic to what you had originally. This is your kinematical data, and these are the adjusted curvatures. So again, you can essentially calculate everything as before. But we should have that because that will also be a vital check mathematically if our model is really consistently defined. Okay, and now let me come to the adjusted parallel transport. So ordinary higher parallel transport that requires fake flatness f equals 0, which is a problem. However, there's quite a few physics arguments that tell you that the 2-0 theory should involve observables, which are Wilson surfaces, so we do expect a consistent higher parallel transport there. And from our lesson before that we said, okay, if I do this adjustment, it cures all our woes with the fake curvature condition, we just say, well, adjusted parallel transport should work, right? There should be an adjusted version of parallel transport. And indeed, that's the case. So I'll take you now through the details. So usual functorial prescription on parallel transport is the following, that you take a path groupoid and a functor into the group, seen as a one-object groupoid. What does that mean? Well, you have locally, we work locally, global things, you can glue these things together, but the interesting thing happened locally. So you have your patch of your manifold, and then you consider the paths as morphisms, right? I mean, you have the two endpoints, you consider them as morphisms. You consider always your group as the morphisms of a point, where for each group element you have a morphism, and then you can just consider a functor that takes you from here to there. And that is essentially parallel transport, right? That's sufficient because it tells you that if you compose paths, you should multiply group elements, and that's it. There's a few technicalities I'm shoving under the rug because they're boring. It's, you have to mod out by thin homotopy equivalence, and you have to impose sitting instances of your paths. But that can be done, that's not an issue. So composition of paths leads to group elements, and that gives you then your definition of the parallel transport. And the connections are seen really as, if you look at infinitesimal paths in the direction x, then you can extract the connection. Conversely, if you have a connection, the path ordered exponential will give you the group element that you should assign to path, right? So this is quite familiar. This readily extends to high gauge theory, and Urs and Konrad Waldorf have papers on this. You can define these higher path groupoids and high gauge groups. You can regard them as one object high groupoids. But again, the condition is always that all these fake curvatures, so all except for the top curvature, should vanish for consistency of the parallel transport. And of course, that's a problem because we saw that this kills our theory essentially. So what can we do? Well, the ordinary parallel transport sees only connections, but we adjusted only the curvature. So somehow we have to get the curvatures into the picture. And then we recall that there's this following sequence of groupoids. So I can look at the group itself trivially as a groupoid, just by saying, okay, I have just identity morphisms, right? Then you, just as in the way that every set is trivially a category, every group is trivially a groupoid. And this can be embedded in the inner derivations of this groupoid, and then I have a further projection onto the group now seen as a one-object groupoid, right? So there's this short exact sequence. Yeah, so in G is the integration of the Lie algebra corresponding to the Weil algebra. So that's the first time that we see why, if we adjust the Weil algebra, we want to consider this. Because if we do an adjustment here, we should kind of translate this into Lie algebra, integrate it, and then we know what we get here. And now we can use this sequence in the following way to extend the functor, which is already in Urs's paper. So it's called, I think we called it derived parallel transport functor. So you look at the path groupoid functor to BG, that's the ordinary parallel transport. But now I extend it along the sequence, so I say now instead of just having BG, I look also at B in G, right? And extend this from the path groupoid to the two path groupoid, so I also fill in every loop by an additional surface, right? And then I have a strict two functor from here into B in G. And then you have the final element which just sees the curvature. So this functor here sees both the curvatures and the connections. However, it's completely determined in terms of the connections, right? If I know the functor for the connection, this just lifts uniquely to this functor, right? There's no freedom in here whatsoever. So this functor is in ordinary parallel transport. This is fully equivalent to this one, right? So they don't see more. It's more that it's just that you expose the curvatures in a sense, so you can really see them because now you have also the surfaces over which the curvatures are, right? Yeah.
Is there a physical intuition for why there's a unique way to sort of covariantize with a curvature?
Well, in a sense, the top curvature is really given to you, right? I mean, if I know the connection, I know the curvature for ordinary gauge theory, right? So there's a case for ordinary gauge theory. So there's not really any adjustment that you would want to do in the Weil algebra at all. So there's no freedom there to do this adjustment. Yeah, I mean, what you do here, I mean, physically, of course, you have the paths, right? And now you extend also by surfaces, right? And then on the surfaces, you have your curvatures, but they're determined via the non-abelian Stokes from the boundary, right? This is what's happening here, essentially. Okay, so what do we need to do if we want to lift this all to higher? Well, now we have a higher gauge group. We need to find this higher G and this one, so this definition. And then we need to lift up to B in G and find the appropriate diagram here. Okay, so we need to find this. So we need to find the inner derivation higher Lie group for a two-group G. And what we note is, of course, that the inner derivations, that's just a Lie algebra that's dual to the Weil algebra. We adjust the Weil algebra, we get a corresponding Lie algebra. in the ordinary case, right? And then we can integrate this. Thus, what we need to do is we need to integrate an adjusted Weil algebra, right? Remember, we changed the Weil algebra, and now we get adjusted inner derivations, and we should integrate that, and then we have higher power transport. Because we use finite constructions, so we want to glue things really not just infinitesimally, but we have finite gauge transformations and finite descriptors. We have finite paths, finite group elements. Everybody who is sane would use a strict model of the L-infinity algebra, not the skeletal one, or not any other model that's not strict, because as soon as things become non-strict and you have associators and so on, things become really, really ugly. It's very, very hard to keep track of things. So we just go to the strict model, but structure theorems tell us any L-infinity algebra has a strict model, so we're fine, right? So that can always be done. Then you see that a general adjustment is possible, and yeah, now I take a simple example just to illustrate the construction that shows you all the details that are going on. Okay, so long slide. So for simplicity, we drop the central extension in our description of the string Lie-2 algebra because you see already everything that's happening in this one, right? So we just take the based paths and the based loops, and then we have in our adjusted Weil algebra, we have generators for each of them, right? So we get T alpha tau, T hat alpha tau for this one, that's a shifted copy, and R alpha tau for the loops, and R alpha hat tau for this one. The action of the adjusted Weil differential, you can compute this, looks like this. And there is this function here that does the adjustment. And that's an interesting function because it takes any path and actually projects it in a certain way onto loops. So that has a very, very specific meaning. What you can do then, you can do a clever coordinate change such that your coordinates become much simpler. You have to be very careful with this coordinate change because we mix non-shifted generators with shifted generators. And what that means is that we mix curvatures with gauge potentials. And what that means is that we have to be careful how we define gauge transformations, because gauge transformations are defined by partial flatness, and if we change now mix gauge transformations with curvatures, gauge potentials with curvatures, then the notion of gauge transformation changes. However, just for the purpose of integrating this Lie-3 algebra, I can do that, right? I just want to integrate, and then I have to be careful later on, okay? Okay, so the result of this coordinate change is a strict three-term L-infinity algebra that just looks like this. And so this is what you have even before coordinate change. It's just now the mu1s are a little bit nicer, and also the higher products are a little bit nicer. And now I just need to quickly recall a little bit to connect it why this is a nice construction. So there's something called hypercross modules, which are essentially these strict versions of higher groups. So they correspond to simplicial groups, and they have trivial associators, so everything there is nice and under control. In principle, you don't have any further obstruction from the highness of the group to integration. So you can integrate these in principle. So as soon as you know you have them, it's not harder to integrate than ordinary Lie groups. So cross modules of Lie groups correspond to strict two-term L-infinity algebras if you differentiate them. So at the Lie algebra level, there's strict two-term L-infinity algebras. So here, there's a nice one-to-one correspondence. However, now we work with 3 Lie algebras, right? You saw that we have here 1, 2, 3 terms, so Lie-3 algebra. And we have to be a little bit more careful. There, the correspondence is more involved. So a 2-cross module, if you forget some structure, you always get a strict 3-term L-infinity algebra. On the other hand, some strict 3-term L-infinity algebra allow for an extension to 2-cross module, right? There's an overlap of these two, but it's not that one is completely included in the other, as it's up here, right? So if you want to compare them, you have to be a little bit careful. So the strict 3-term L-infinity algebra we get from the adjusted Weil algebra. So the thing that we want to integrate happens to be precisely 2-cross module. So that's one of the ones that we can extend really to a 2-cross module. And not only that, but this extension data that's missing here, that's the Pfeiffer lifting, or rather the symmetric part of the Pfeiffer lifting, I should say, that is given precisely by the adjustment data. And that's kind of cute, right? I mean, we modified the Weil algebra in such a way that we had this adjustment, and the function that controls the adjustment is precisely what allows us to take this 3-term L-infinity algebra, extend it to a 2-cross module, and then integrate it, right? So that's a nice coincidence. If you want to look at it more abstractly, there's something called EL-infinity algebras that were introduced by Reutenberg for Lie-2 algebras. And if you do everything in here, then it works, right? So these 2-cross modules are 3-term EL-infinity algebras in disguise. Okay, so that's fine. Now we have our W adjusted is a 2-cross module of Lie algebras. We can integrate it to 2-cross modules of Lie groups. Right, so strictly 2 algebra is this thing. The adjusted inner derivation, this thing. 2-cross module of Lie algebras, because the adjustment allows us to lift it, gives us exactly what we need to lift it. And this integrates then to a two-cross module of Lie groups. Okay, so that's quite technical, but I mean, if you discussed a little bit or if you study that a little bit, it's kind of cute that this comes out on the nose. Okay, so ordinary paratransport functor for 2 group G would look like this, right? So you have here your ordinary paratransport functor that it also induces, if you don't modify anything, this one, and the fake curvature condition f equals 0 is there, killing everything, making it useless for the 2-0 theory. On the other hand, if you now do the adjusted paratransport functor, what do? Well, you forget that you had this one in the first place. You directly start from this one into be in adjusted of your string loopy algebra, right? And this functor exists, and you have curvatures, and you can also define what the appropriate notion of gauge transformations is, of course. And now the consistency is no longer fake curvature, but it's the Bianchi identity of the ordinary two-form curvature. And this doesn't come from any ordinary functor. You can't restrict it to any ordinary functor that lifts then up, right? So this part is simply gone. And what this suggests is that you should define paratransport for higher gauge theory really in terms of these derived paratransport functors. Okay, so that was a lot of technical mathematics. So just to wake up the physicists essentially a little bit. How much time do I have left, actually?
We started late. The time is up.
The time is up.
Since we started late,
Okay.
we still have 10 more minutes.
No, okay, 5 more minutes should be enough, right? So this is one of the 3 attack vectors that we now have on this 2-0 theory, and I have a PhD student postdoc in place. If we don't have it in 2 years, then it's over, then I give up, right? Then I agree, okay, so the following thing, 3-level scattering amplitudes for the 2-0 theory have recently been proposed, and everybody seems to be happy with this. But from my perspective is that this means that we have an action. And the story goes as follows, and this gives me an opportunity to shamelessly advertise this paper. It's collaboration with Martin Wolf and Pranyu Yurcho. Pranyu mentioned it already yesterday. So what has been known is that a classical Lagrangian field theory via the BV formalism produced an L-infinity algebra. This is a very, very old fact. It's in Costello, it's in Cacciura, it's ring field theorists know that. Olaf Hohm has recently rediscovered it with Zwiebach. I had parts of this in 2009, but it's essentially all the same story. What you do is you do BV formalism, you encode your gauge transformations, your equation of motion, and it gives you just an L-infinity algebra, right? So this is a fact that people knew for quite a while, right? To certain degrees, right? Yeah. Now, the structural theorem that I mentioned before is that any L-infinity algebra has a minimal model, right? So L-infinity algebras come with minimal models, up to ordinary isomorphisms, actually. And now the statement is that minimal models encode 3-level scattering amplitudes, right? If you compute the minimal model, it's precisely the Feynman diagram expansion by homological perturbation lemma of the 3-level scattering amplitudes. And goes recursively, and you can imply this to amplitudes, which is nice and kind of cute. But then there's also the other structural theorem that I mentioned. Any L-infinity algebra is quasi-isomorphic to strict one, where these higher products essentially vanish for I larger than 3. So you have only a differential graded Lie algebra. So you have only binary product. Okay, so for the 2-0 theory, we have 3-level scattering amplitudes from Bootstrap that have been proposed here, and people seem to be happy to propose these things, okay. So, but then, of course, by this construction, I have a minimal model. I now read it inversely. That gives me my minimal model, and then I can apply the structural theorem to get a strict L-infinity algebra. And what this says, it gives me an action that has only cubic vertices for these amplitudes, right? So in principle, there should be an action. I'm not sure if you see any flaw with this logic from a physical perspective, that if you have 3-level scattering amplitudes, that this should mean that you have some action, then please let me know. So we obtain action with cubic vertices, and the goal is to construct the strict and other actions, of course. So essentially we're inverting this homological perturbation lemma because we kind of know what kind of field content we want, in which quasi-isomorphism class representative we want to have. And so we can invert that to a certain degree. Okay, so let me sum up. So we did a few things. It was very technical, so should apologize to the non-experts about that. So, but we do have metric string structures. We do have the correct notion of higher algebraic structures that we want. We do have the corresponding connections in all kinds of variants. We replaced PST with sense mechanisms. So the action is actually in reasonably good shape. It has physical problems, but these are the next to attack. So we need to complete some calculations here, and then we get hopefully general actions from amplitudes, and then there's further problems that need to be solved. Okay, thank you very much.
Thank you. There was a question here already.
Yeah, I was just going to ask, so you have scattering amplitudes, so what are the asymptotic states?
Yeah, it's a usual problem with conformal field theories, right, that you don't define. I mean, what they mean here, in this theory, you could define what you mean. I mean, the going to minimal models essentially knows what the asymptotic states are. They're just the three solutions to your equation of motion. You just drop all the potential terms, just chop them off. You take only the quadratic terms of your action. So if you take this action, for example, right? So you expand this in the fields. You just take polynomials up to degree 2, throw everything else away, derive equation of motion. That's the asymptotic. That's what the homological perturbation lemma tells you to do. Right, so mathematically it's clear what it means physically at a conformal level, but I think there are lots of arguments how to go around this and what you really mean there in asymptotic states. Yeah.
Well, in n equal to 4 super Young mills, people have been computing amplitudes for many years,
Yeah,
right?
exactly. But the question always comes up, right?
There I know what the fields are and what my asymptotic states. I thought that one of the arguments for the conformal.
Well, I think the point is here that there will be asymptotic states here are as much in existence or non-existence as n equal to 4 super Young mills, right? It's both conformal field theories.
I should finally learn the correct words to answer this question, even for n equals 4. I don't know them yet, but there's, of course, the same problem. Yeah.
Right.
Yeah, just can you say a little bit more about what is the issue with the PST?
Well, yes, exactly. Sorry. I should, yeah, of course, I should ask you actually. I mean, I don't like. Apologies. Yeah, sorry. Oh, wait. Already at unicorns. Where was it? Of course, I don't like this 1 over phi. So how do you make sense of this?
What is phi?
The scalar field. I mean, you have that as well in your paper with
well, phi. There is no phi s in the denominator of the scalar. These Ey which you wrote, they are just normalized vectors. So there is no such term there.
No, but you have it as well. It's hidden by you. You write this M matrix. We can probably discuss it in detail.
There is no this is not a scalar. This is the square root of the normal norm of the divergence of the scalar. So so it's not a Lagrangian multiplier which stays there.
I can probably discuss it on later.
And but anyway, so the V which you wrote there is just the gradient of the normalized gradient of the scalar.
Yeah,
and that's it. There is no anything else.
Yeah, exactly.
If you don't like the that there is a normalized gradient, you can introduce Lagrangian multipliers, and the action will be polynomial.
No, I have lots of questions about this. I should really talk to you in the break.
So
Let's maybe discuss in the break, because we want to stay in time for the excursion this afternoon. So let's thank maybe Christian again.
Thank you.